Today's is going to be the last on the series on diodes. Let us therefore sort of discuss what is left on topic connected with diode and also summarize the whole thing. We will also try to understand some special diodes which has specific application, just like Zener diode for example. Consider the PN junction. This is the semiconductor diode. I have told you earlier, by formulating a PN junction like this, we are able to get the IV characteristics that is pretty close to the ideal diode. The IV characteristic being the exponentially related characteristic between current and voltage. Now, apart from that, we would like to see what other terminal characteristics the diode represents. When it is a PN junction like this, at the junction we have a region depleted of carriers, free carriers. This region is called depletion region. The P side comprises of free carriers which are called holes. N side comprises of free carriers which are called electrons. Since they are free carriers, the moment they are brought together, junction is formulated, they have a tendency to merge one another. Hole has a tendency to merge with the electron and vanish. Okay. Then this region at the junction becomes free of carriers. Thereby it develops a potential hill. This is called the junction potential, V junction. And this V junction, according to the semiconductor theory, for silicon happens to be around 0.5 to 0.7, we said. That is why the semiconductor diode was not exactly close to ideal diode. There is a deviation from it. It starts conducting only when a junction potential of about 0.5 to 0.7 volts is applied. The current is unlimited. Until that time, current is negligible. So, this region where it is depleted of carriers is called depletion region. So, every PN junction has a depletion region in between, and this depletion region width is dependent upon the voltage. When the junction gets forward biased, okay, the barrier, the potential hill for these carriers decreases. So, there is copious amount of free carriers moving from this to holes from moving from this to this and electrons from moving to this to this, and that constitutes a current. Large current can flow. Whereas, when it is reverse biased, okay, there is this potential hill increasing. The reverse bias will help this potential hill to get increased. That means more area in this gets depleted of carriers, okay, and this region widens. So, this depletion layer width is dependent upon the bias. When it is forward bias, the depletion region width decreases enormously and junction width decreases enormously, and this, when it is reverse biased, increases. Now, since it is a depletion region depleted of all carriers, we can consider this region as equivalent to two parallel plates within which we have sandwiched an insulator. Okay. No carriers exist, so it is an insulator. So, it is equivalent to a capacitance. When it is reverse bias particularly, we know that current is not flowing at all. That means the reverse resistance is very nearly infinity, but it can be now equated to a capacitance, not just an open circuit, but capacitance really. Therefore, we can always say that a junction diode under reverse bias condition, apart from being considered DC wise carrying only the reverse current, can be also constituted to have a capacitance which is dependent upon this. So, if the depletion layer width is, let us say, d, then the capacitance is epsilon. Epsilon corresponds to that of silicon, okay, divided by d into area. The normal way capacitance is defined, parallel plate capacitance, is nothing but the distance between the parallel plates, which is d, okay, coming in the denominator, epsilon, okay, into area of the capacitance plates. So, this constitutes the effective junction capacitance, and this depletion layer width is dependent upon the reverse bias voltage that we apply. And therefore, if we apply a reverse bias voltage which is very large, depletion layer width increases and therefore, the capacitance decreases. So, this kind of property of the junction, if it is exploited, then that particular diode becomes a special diode. Okay. You can say it is a diode specially used for its capacitance, and the capacitance is now going to be dependent upon the reverse bias voltage. As the reverse bias voltage magnitude, let us say, increases, I am now having the circuit here. This is our usual diode symbol, and I just put a resistance here saying that it is a network. This resistance is not going to matter now, because no current is going to flow through this, because it is reverse biased. So, according to us, the current through this is 0, or it is equal to the reverse saturation current, very small. But therefore, the voltage across this is going to be very near the voltage that I have applied. So, the magnitude of that voltage is going to determine the value of the capacitance. As the magnitude of the voltage increases, the capacitance decreases. This kind of nature, the capacitance is of the order of picofarads. Okay. So, this diode therefore is called varicap or Varactor diode. Varicap, variable capacitance. So, either you call it varicap, variable capacitance, or Varactor diode. So, I have now given you the typical characteristic of commercially available Varactor diodes, 3 of them, compared with conventional diode, whose variation from maximum to minimum is not going to be significant, because it has not been manufactured for the purpose of using it for its variable capacitance. Whereas these have been specially taken care to see that the capacitance variation is maximum for the voltage that is changing from maybe 0 to 25 volts, typical change in bias voltage of these variable capacitors. So, maximum to minimum you should have normally as high a ratio as 5, typical. It is a good Varactor diode, and the maximum value of the capacitance itself depends upon the frequency range where you are likely to use it. Can be due to construction, it can be made to vary, right. If the area is increased, it can be higher. So, C max can be anywhere from 5 to 300 picofarads. This is for a high frequency application, this is for typical low frequency application. So, this is one of the most important uses of diode in its range, that is reverse bias, but before breakdown. Now, let us make ourselves clear. The diode has, the ordinary diode has the forward bias region, the reverse bias region. In the reverse bias region, we have the breakdown. This is the forward biased region. Then this is the reverse bias region. Here it is having infinite resistance in this region. It is in this region that it is used as varactor. It is in this region it is used as a rectifier diode. It is in this region it is used as a varactor. It is in this region it is used as a Zener diode. So, in the case of rectifier diode, we are not so much bothered about its use in the reverse bias region where the resistance is infinity. There is going to be capacitance, but its variation is not going to be much. This is the conventional diode. So, if it is a power diode, the area is going to be larger and the capacitance also is going to be higher. If it is a small signal diode, the area is going to be smaller and therefore the capacitance is going to be lower. But therefore you have to remember that power diodes, okay, sometimes should not be really used for high speed applications because the capacitance of it is really very high. So, that means high frequency rectification, you should not use conventional power diodes which are used for 50 hertz. This is the normal confusion that exists. For rectifying a high frequency waveform, we must never use a power diode because it is going to still conduct, okay, because of the capacitance. Therefore, this kind of thing we should be very careful about. In this region where it is neither breaking down nor going to the forward region, when it is biased properly, it can be used as a capacitor. Where do you use this variable capacitor or Varactor diode? Whenever we want an oscillator, okay, LC oscillator, we will discuss this later, okay, whose frequency of oscillation has to be varied by varying a voltage controlled oscillator, voltage controlled oscillator can use this variable capacitor, or a filter which has to be tuned, voltage controlled filter, voltage controlled oscillator, all these things use this Varactor diode for varying the capacitance of the network, thereby vary the frequency of oscillation or the frequency of the filter. So, this is the application. We will later see how we can utilize this. Finally, the Zener diode has already been discussed. So, you can see that the manufacturer will concentrate on its use as a Zener diode, then the breakdown voltage is going to be within a certain percentage accuracy. Okay. Here he will maximize the ratio between C max to C min, okay, and specify what value of maximum capacitance it has, and then here he will say at what forward current it has to be operated, what is the average forward current, repetitive forward current, okay, all these things when it is being used as a rectifier diode. What should be the peak inverse voltage rating of this if it is to be used as a rectifier diode? These are the different ratings. So, different diodes have different emphasis on the ratings. Okay. So, we will now discuss other variety of diodes which are not extracted from the same characteristic, but which may have different sort of material used for the fabrication, different characteristics, okay, as special diodes. So, continuing with our discussion on special diodes, Varactor diode, the symbol is that of the ordinary diode with the capacitor put alongside. Okay. Sometimes the capacitor is put at this point also. Either the capacitor is put alongside the diode or along with the diode here in line with this diode. So, that is the symbol for the Varactor diode. Now, let us consider another important diode which is called photodiode. What is it? Again we can go back to our PN junction. The PN junction has certain amount of leakage current in it, that is the P material has majority carriers which are holes and minority carriers which are electrons. Here we have majority carriers which are electrons, but minority carriers which are holes. Even though for the holes here as well as the electrons here there has been a barrier potential hill corresponding to 0.5 to 0.7 I said, because of the existence of the depletion layer. This is happening the moment I formulate the junction. For us to have an equilibrium here, there is a potential hill created. Now, this particular junction is still permitting the minority carriers from here to easily go to this, because this potential hill which is an obstruction for the majority carriers is a sort of an aid for them to flow freely. So, there is a field here which will help these minority carriers from moving from here to here, okay, and the minority carriers from moving on here to here. This minority carrier flow obviously will increase if this hill for the majority carrier increases, but there is only a maximum limit because these are all saturation value corresponding to the saturation current it will reach. Ultimately the current when it is reverse biased, okay, that will be flowing only because of this kind of current due to minority carriers. This is called the reverse saturation current or leakage current, and that gets saturated at a value Is for the diode. So, for a conventional diode we know that this current in the reverse bias is 0 for 0 bias and gradually increases and reaches a saturation. If you magnify this several times, this is the way it will get saturated at Is. Is is I diode is equal to Is exponent V by eta Vt. This is the usual expression that we have been using. This is the reverse saturation current. Okay. So, it reaches saturation. This is of the order of maybe picoamperes or even less for the silicon diode. Now, what happens if I make light fall on this junction? So, that means there should be a facility to expose the junction to light. So, that is the constructional feature of a photodiode, where this junction is physically exposed to light, which means these diodes will have a sort of glass window which will expose the junction directly to light. That is the only difference in constructional feature for these photodiodes. Is it clear? Now, if light falls on this junction, that will create further carriers, right. This will give enough energy here to break bonds and create free carriers. So, the carriers here will increase. So, this energy is a source for creating more carriers. So, that means more current, such reverse saturation current can be sustained, okay, for the same reverse voltage. That means the characteristic will now look like something like this. So, basically remember that you are increasing the reverse saturation current and providing a sustained reverse saturation current, okay, of increased magnitude by giving an energy here, light energy here. So, this is the source from which it gets the energy. So, this particular diode characteristic now will be like this. This is the reverse saturation current saturating here. Not only that, because it can be sustained like this, it is going to have an open circuit voltage, because this current is 0. This open circuit voltage if the intensity is large enough, gradually goes towards the 0.5 value for silicon. Okay. So, this is the open circuit voltage, and therefore, it can be used as a voltage source, a battery. That function of this diode, photodiode, is known as solar cell. That battery, which you can sustain by giving an external source of energy to the junction constantly, that junction voltage for silicon is typically around 0.5, and you can now have a battery of your own. Okay. So, this is an important application of photodiode as a solar cell. Obviously, in order to collect lot of light, you must expose the entire area of this junction, okay, to light. So, that is the constructional feature of the solar cell as distinct from a photodiode. Right? Photodiode also requires lot of light, but in the case of solar cell, the efficiency you want it to be optimized. Okay. So, you will take care to see that maximum area of this is exposed to solar. So, you will increase the area, large area, okay, photodiode becomes nothing but a solar cell. So, these solar cells can be stacked in series, okay, as well as in parallel to constitute a power pack, which can deliver power to your satellite or anything you want, okay, whenever there is light energy falling on it. So, in all your satellites, you will have the mounting of the solar cell panels always sort of controlled and pointing towards the light source, okay, the sun, for example. And then if the light is not there, it can be sort of charging a battery so as to conserve energy when the light is not falling on it. Okay. Now, this is the way the saturation current varies depending upon the various illuminance level, right. Illuminance is increased. Okay. So, in this direction the current capability here, right. This is open circuit voltage, this is the short circuit current. This value of current is going to be the short circuit current, and this is the open circuit voltage for this photodiode or solar cell. And the symbol for that is just the ordinary diode with light falling on the junction indicated by arrows. So, light is falling on the junction is indicated, that is a photodiode symbol. This can also be used to convert light energy into electrical energy. Okay. Also measurement of light. For measurement of light you can use this as a transducer, apart from using it as a battery. These are the various important applications of photodiode. Now, let us go to another diode which is almost sort of a counterpart of this photodiode. This is called light emitting diode or LED, popularly known as light emitting diode. So, the symbol is when this is forward biased, this junction, see, remember that there this is the reverse bias saturation current which is controlled. Here this junction, when it is forward biased, okay, under forward bias condition this emits light. It is important. But such a diode is not a silicon diode, it is made out of not group 4 element which is silicon, 3,5 compound element which is called gallium arsenide or gallium arsenide phosphide or gallium nitride, gallium phosphide. This material, okay, when a p-n junction is formed using this compound 3,5 compound in the periodic table, okay, silicon is group 4, this is 3,5, and when it is combined like this and a junction diode is formed, p-n junction diode is formed, then that behaves like an LED if sufficient forward current is applied, typically 10 milliamperes or so, right, and the typical voltage, forward bias voltage. Now please compare this with the forward bias voltage of a silicon diode, which is of the order of 0.5 to 0.7 we said, at currents of the order of milliamperes. Gradually it might become 0.8 to 1 as it goes to higher currents, right, but here it is greater than 1, right, for 10 milliamperes itself 1.5 to 1.5 volts. These values, typical values, you should know in order to bias these so that they can emit sufficient intensity of light. So the light intensity obviously depends upon the current, magnitude of current flowing through it. Okay. So the color, for example, infrared, okay, not visible. This is very useful for defense applications. Okay. There is light, but it is not visible to the human eye. So this is commonly used, okay, for military applications. Infrared, red, infrared 6, that is 900 nanometers, okay, that is the wavelength of this particular light, and gallium arsenide is the material which gives you this color, okay, and the forward voltage is 1.5 to 1.3 to 1.5 volts. Second, the red color 655 nanometers, gallium arsenide phosphide is the material, 1.6 to 1.8 volts. Yellow color 583 nanometers, again gallium arsenide phosphide, 2 to 2.2 volts is the forward voltage at 10 milliamperes. Green color 565 nanometers, gallium phosphide now 2.2 to 2.4 volts forward voltage. Blue color 400 nanometers wavelength, gallium nitride is the material, and 3 to 5 volts is the forward voltage. So you should know these typical values for different colors so as to design a circuit to bias this so as to emit light. Where is the application of this? Obviously all the display units. For showing you the different numbers, okay, or letters, etc. These are called, there are different types of displays available. This has 1, 2, 3, 4, 5, 6, 7. This is called 7 segment display. Each segment can be an array of LEDs, okay, so as to form this kind of segment. And for example, typically I want 3, number 3. So, this will glow, this will glow, this will glow, this will glow, this will glow. Right. So, by a control circuit you can get all numerals using this kind of 7 segment display. Another display is called dot matrix, okay, so that you can get both numbers as well as letters, okay, being displayed. So, this is the important application of LED, but slowly these displays are going to getting replaced by what are called LCDs. This have nothing to do with diodes, okay. These are called liquid crystal displays, okay. However, primarily the reason is you can see the amount of power dissipated, okay, 10 milliamperes, okay, into let us say 1.5 volts is going to be 15 milliwatts, okay, just to sustain an LED. So, it consumes too much power. So, even though before the advent of LCDs these were being used for displays, right, with the advent of LCDs, okay, these have gone out of use for most of the cheap displays like wristwatch display, etc. We cannot afford to waste current, okay, and power of this order of magnitude, okay. So, however, for large displays and things like that, you do not mind, okay, wasting some amount of power on this display, these displays are still being used. Now, a combination of photodiode along with the LED to detect light, that is LED to emit light corresponding to some current, let us say. This is the current flowing in some circuit, assume. Corresponding to this current, some amount of light is going to emerge. This light, let it fall on another photodiode. So, let us say this light is made to fall on a photodiode. So, this is an LED, this is a photodiode. So, the combination is an important unit in present day electronics, particularly with this optical fiber coming into picture, etc. Right? This becomes an important unit where this light itself, which is generated by a current, can fall on this photodiode and generate a corresponding current. So, this current which is generated here is dependent upon this current. This light magnitude intensity is dependent upon this current, okay, and the current generated here depends upon the luminance level of this here. So, in turn we have generated a current dependent upon this current, and these two are perfectly isolated. So, this can be in one circuit and this can be in another circuit. This can be in, let us say, high voltage circuit, this can be in the low voltage circuit, which is measurement circuit. So, this is an isolator, this is an opto isolator. Or this is also called opto coupler. This can couple as well as isolate. This will couple this signal to this. This will isolate this signal from this circuit from this circuit. So, these are called opto couplers or opto isolators. Important units like this are available for a variety of application, okay, where you would now rather not use transformers and things like that for isolation purposes. You would like to use some electronic element like this which is quite convenient. Very intelligent designs are available where this can be used for precision measurement of current in high voltage circuits, etc. So, this is another application of this combination of photodiode with light emitting diode, which is called optocoupler or opto isolator. Now, you are going to be shown some of the diodes which are used in practice. Consider this. This is a small signal germanium diode. You can see very small size, and its specifications are that it can tolerate a forward current of the order of 50 milliamperes, which is quite small you consider, and reverse voltage of about peak inverse voltage rating of about 90 volts, and the forward drop is considerable. This is apart from the junction drop, also there is considerable amount of series resistance drop here, about 1 volt. And the next one is a small signal silicon diode, again operating current maximum, forward bias current maximum is of the order of 200 milliamperes. Peak inverse voltage rating is about 100 volts, and it is supposed to be a fast diode, and therefore this recovery time, this from forward bias mode to the reverse bias, okay, there is a delayed time of the order of 4 nanoseconds. This is important in diodes which are used for switching applications. It should be kept very small, and when it is forward biased, the typical voltage at the currents of the order of 200 milliamperes is about 1 volt. Finally, in this we have a power diode. You can see the size compared to the other ones. This size is bigger, right? And it can carry a current of the order of 1 ampere, and its peak inverse voltage rating is of the order of 1.2 kilovolts. Okay, and this is what I had discussed when we designed our rectifiers. Okay, the forward current that is of the order of 30 amperes it can sustain, and Vf maximum is of the order of 1.5 volts. You can see therefore that the forward voltage is taken as about 0.5 to 0.7 only when the current is very small, of the order of milliamperes or less. Otherwise, okay, at currents of the order of 30 amperes, apart from the junction drop, the series resistance drop also comes into picture, and it is of the order of 1.5 volts. This is a power diode BY127. Now, you consider a series of Zener diodes being shown to you. As the size itself indicates, this is a low power Zener diode, 400 milliwatts, 3.9 volts. Okay, 3.9 volts is the breakdown voltage of the Zener. Next one is 5.6 volts breakdown voltage, but higher wattage, 1 watt Zener. Okay, slightly bigger in size. Okay, 1 watt Zener, power rating is higher. The next one is really a power Zener, okay, 13 volts Zener with 3 watt power maximum dissipation permissible. So, you can see the size comparatively bigger in size compared to the other ones. The next one is another power, this thing, it is 6.8 volts, 10 watts Zener diode. So, all these things can be really used as secondary sources of power. Okay, maximum power it can dissipate is 10 watts, and the voltage is for regulated voltage of 6.8 volts you can use for power supplies. So, you can really use it for large current output. Coming to special diodes, we have now here a Varactor diode. As you can see, the nominal value of the capacitance C total is 20 picofarads. C1 by C2, that is maximum to minimum ratio, typically is 5, I said 4.5 in this case, okay, and the maximum voltage that you can apply is 30 volts. Okay. So, this is BB 109, which we had also plotted in the earlier class, okay, Varactor diode. The next one is a light emitting diode, LED, red color. This also we had indicated. The IF max is 30 milliamperes, that is maximum current that you can apply on the forward bias mode, and the voltage drop maximum corresponds to about 3 volts at that point. IF typically is 10 milliamperes and P naught max is about 100 milliwatts, maximum power dissipation permissible. Peak wavelength is 635 nanometers for this LED. Now, you can see the solar cell that we discussed as a photodiode. Okay. We have a series of solar cells connected in series and parallel, forming a panel, glass panel here, okay, so as to collect maximum amount of light onto the surface of this. All the junctions are exposed here, okay, and finally all these are connected in parallel, series and parallel, and coming out as a 2-terminal, okay, solar cell. Okay. We have the 2 terminals brought out. Okay. Yeah, we have the 2 terminals brought out for the composite structure which is formulating the solar cell. We have some other diodes like Schottky diode, which is not a semiconductor PN junction as we had discussed earlier diodes. It is a metal to semiconductor junction. What is the advantage of this? Unlike the silicon diode or germanium diode for that matter, this PN junction diode has a forward voltage which is 0.1 to 0.2 volts. It is much less than the forward cut-in voltage of silicon, which is 0.5 to 0.6 volts. So, that means it starts conducting much earlier. So, it is closer to the ideal diode in its forward characteristics than these other semiconductor diodes, and also it is having a sort of delay time which is of the order of nanoseconds. So, it is a high speed diode. So, these diodes specifically are used for high speed switching applications, okay, and also in preventing, later on we will see, a transistor from going to deep saturation. In fact, therefore, you have all high speed circuits with Schottky diode connected between collector and base of a transistor to prevent it from going to deep into saturation and becoming slow. So, for high speed applications, this Schottky diode is used, which is a metal to semiconductor junction. Apart from this, we have tunnel diode, which is typical 2-terminal diode with negative resistance, which is also usable for very high frequency applications, but unfortunately it's because of the difficulty in fabrication of that, its application has become obsolete now, and very few people are using such tunnel diodes. We have some typical application in power, okay, where diode is used as a protective element. I would like to elaborate little bit here. We have an inductor L, let us say, in which a current I is flowing because the switch is closed, right, current is flowing in an inductor. Let us now open the switch. Such a situation exists in switching on a relay coil and switching it off. So, this is the relay coil, assume. The relay is operated by injecting a current into it. So, relay has the inductor, the current is flowing in the inductor. Now, I am disabling the relay by trying to open the switch. the voltage across an inductor is L di by dt. The current therefore suddenly here becomes from I to 0, sudden drop in current. So, that means di by dt is infinity. That means voltage across the inductor becomes infinity. What does it mean? That when I am trying to open this switch, right, this current tries to continue to flow, okay, because current in an inductor cannot be changed suddenly. That is mainly because di by dt rating you are trying to force it to 0. If you make it 0 actually, that means di by dt is enormous. It is changing suddenly from finite value to 0. Okay. So, the voltage across the inductor, induced voltage across the inductor is suddenly going to very high value. Then the voltage across the switch, okay, goes to that higher value, open switch, that just breaks down. There is arcing here. There is arcing here. Okay. Why the arcing is there? The current continues to flow. Arcing indicates the current is trying to flow, right, so as to prevent this from happening. So, this kind of situation damages the switch. The arcing will damage the switch. How to prevent such a thing? Such a situation, it is advisable to put a protective diode across the inductor, so that this current is, when this switch is opened, this current continues to flow in this circuit. So, earlier this circuit has a current injected through this, the current through the diode, okay, is 0 because the diode is reverse, okay, biased. So, the current cannot flow through the diode in this direction. But the moment the switch is opened, the inductive current now can flow through the diode like this. It will flow through the diode until such time, okay, the entire energy gets dissipated in this circuit itself. Okay. So, this kind of structure will prevent the switch from getting spoiled. So, this is a protective diode which is invariably introduced in almost all power circuits where there is an inductor and through which there is a current, a steady current flowing through the circuit. Okay. So, this kind of application in a relay coil, okay, to prevent the switch from getting damaged is quite common in power electronics. With this we conclude the series of diode, its characteristic and applications. We have covered almost all applications of the diode, starting from its application as a switch, control switch, to its application as a transducer, semiconductor diodes as a transducer. We have covered considerable number of applications. I hope that this will be the foundation for the next chapter on basic electronics, that will be the 3 terminal elements. This is a 2 terminal element, 3 terminal elements starting with transistors.